Okay, guys, we're gonna be doing still exam one review, but part two this time. And this one's all about conjugation, Diels-alder, electron withdrawing groups. It's a lot of thermodynamics, and then there's the hybridization stuff. So that's what we're gonna be going over in this page. And I'll be sending you guys a copy of this so you can work along with me. But for number one, which of the following compounds is more stable? Provide your reasoning using an energy diagram. So for the stability of these two compounds, what I'm looking for here is conjugation. So conjugation is at least 3 consecutive sp2 atoms. So what I'm going to do is I'm going to label all my sp2 atoms is right here, right here, right here, and right here. And on this next one, this carbon is sp2, this carbon is sp2, this one's sp2, and this one's sp2. Okay, so conjugation again is at least 3 consecutive sp2 atoms. So we have 1, 2, 3, 4. This one is conjugated. On this one, we have 1, 2. Skipping a carbon, so that's not consecutive conjugation. And again, we have 1, 2, skipping a carbon, so no conjugation on this one. So when it doesn't have conjugation, when your compound doesn't have conjugation, it's called isolated. There you go. And so how we would explain this is using an energy diagram. They're probably going to make you draw at least one energy diagram on your test. So just know the axis titles and everything. So it's reaction coordinate. And this one, the y-axis is energy. And so we're coming from, these are two different reactants. This whole compound is way different from the one on the right. So we're starting with two reactants. One of them is going to be more stable, meaning lower in energy. And I'll call this compound A, compound A. So let me trace it again. And then this will be compound B. It starts off higher in energy, meets and makes the same product. Same product. So the only difference in this energy diagram is going to be the reactants. So just showing which one is more stable and not. But they're both going to give you the same product because this is basically showing you like the heat of hydrogenation. So I don't know if you guys remember this. Palladium on carbon. And all that does is gets rid, let me just write another one or something. All that does is get rid of the double bonds. So it's just a plain thing like this. So if you do a heat of hydrogenation of both of them, palladium on carbon, you have 1, 2, 4, 5. It's the same thing, heat of hydrogenation, get the same compound. So since we're getting the same product, that's why they're meeting up right here. Same product. Okay, cool. Let's move to the next one. Provide the products for the following Diels-alder reactions. My biggest tip for this one is numbering your carbons. That's what's going to get you. At the end of the day, what gets most students is like knowing how to orient your substituents. So let's try it. Just numbering will help you already. 1, 2, 3, 4, 5, 6. I'm numbering all the things that are going to be reacting in the Diels-alder reaction. So I'm going to break this double bond and form a carbon bond to the carbon number 6. Break this double bond, form a bond to carbon number 4. And there can't be 5 bonds on carbon number 4, right? So then we have to resonate this double bond over. So it's a concerted mechanism. And it's always going to make your cyclohexene. So number your carbons again, just to make sure that we're all good. There we go. So the double bond resonated between 2 and 3, and we got that covered. So let's try this next one. Change colors. Remember your carbons, everything reacting in your reaction. Break the double bond, form a carbon-carbon bond. Break the double bond, form a carbon-carbon bond. Can't be 5 bonds on this carbon, so I resonate. We're always going to be making your cyclohexene. Remember everything. Double bond between 2 and 3. And now we have to orient our substituent. So notice how on carbon number 6, I have a methyl group. And on carbon number 5, I have another methyl group. Now, the important thing here is knowing whether to, or how to orient them in space. So whether you want it on dash and the other one on a wedge, or both on a wedge, or both on a dash. And so how you would determine that is you just look at your dienophile and you determine if it's trans or cis. So this dienophile is trans, meaning if I put one methyl group on a wedge, I should put the other methyl group on a dash. Since they're trans, they're oriented 2 different ways. Okay, let's try this next one. Number your carbons so you don't drop anything. Break the double bond, form 1. Break double bond, form 1. Everything is concerted. Form your cyclohexene. Number your carbons. And then how are the CF3 and NO2 groups oriented? They're in cis conformation. So then since they're cis, they're either both going to go on a dash or both on a wedge. So you can draw either this or this. And then I would usually forget to actually add the substituents that we have, just like I did on the left one. So make sure that you write in your CF3 and NO2. There we go. Make sure you're good so far. Yeah. Okay. This next one can get a little tricky. So when we usually see the 1, 3, or the diene in a open conformation, but here they're giving it to us in a closed, like it's closed right here. So that's not something we normally see, but when you see that closed ring and you know that it's a Diels-alder, you know that you should form that weird bridge form. That weird bridge form. Okay, so I'm just gonna make it look a little bit prettier. Remember my carbons, only the things reacting in my reaction. So if this was open, then this would be carbon 1, 2, 3, and 4, 5, and 6. Draw my arrows. This bond is breaking, forming a carbon bond here. This double bond is breaking, forming a carbon bond here. Resonate this over between 2 and 3. Now I'm going to number my carbons on the bridge. 1, 2, 3, 4, 5, 6. Cool. So I resonated a double bond between 2 and 3. So you put your double bond. The only thing that we're missing here is this carbon that we didn't include. This one right here. So what we're going to do, that was a bit too big. This carbon right here. What we're going to do is we're going to draw a bridge on here. Here we go. Let's see if I can draw this okay. There we go. So what that little dot on the top represents is a carbon. Every vertice is a carbon, right? And so you can kind of see that the diene, the tip of it popped up to make that new bond on the bottom. So it's a normal pentadiene, and it pops up to make these new bonds. Okay. Last one. This is another good example of why we should number our carbons. So right here, it looks a little bit different. It's in the trans conformation. So what you have to know here is, or what you have to write down here, is how the substituents, let's see. Yeah. You look at your diene and notice that your substituents are facing on your double bond, are both facing up. That's usually a cis, right? So another word for cis is Z, which was, remember, same side. So these two groups are on the same side of the double bond, right? So I'm gonna put Z. Then I look at my other double bond. These two groups around it are on the same side, so this one is Z as well. But now I'm gonna make it look pretty. That was like one of the important things we have to write down before we put our substituents on the cyclohexene. But now we have to see what our cyclohexene looks like. So I'm going to write what we usually see. The diene. I'm gonna number it up here first because I'm gonna get confused. Do 1, 2, 3, 4. So 1, 2, 3, 4. Let me add my substituents. I'm gonna point it down so that both of the groups on the two sides of my double bond are still in Z conformation. And then on carbon number 4, I have a methyl group and it's in Z, so I'm going to put it up so it can remain in Z conformation. Then I'm going to just draw right next to it the dienophile. There we go. Now what I will do, continue numbering 5, 6, everything that reacts in your reaction. And now we can start doing our attacks. So this double bond breaks, forms a bond to this carbon. Double bond breaks, forms a bond to this carbon. Resonate. So then your new product should look like this. Always your cyclohexene. That was a bad one, but yes. The number 1, 2, 3, 4, 5, 6. Double bond between 2 and 3. We have substituents on carbon 1, so we have an ether group. So the only thing that matters here is how we orient it in space. So since the two conformations on the double bonds are Z and Z, they both either have to be on the dash, so both of them on the dash, or you can put them both on the wedge, but make sure they're both in the same conformation. So I'm going to put them, this is just arbitrary, so I'm going to do it on the wedge. So on carbon number 1, I have an ether. Carbon number 4, I have just a methyl group. Make sure that they're both on wedge, or if you want, you can put them both on the dash. But you can't have 1 and 1, not for this one. Then for the dienophile, again, determine if it's cis or trans. So this one is cis, so we know they're going to be in the same conformation as well. So decide, do you want them on the wedge or do you want them on the dash? I'm going to put them on the wedge. But know that you're comparing only these two. So since these two are cis, you got to make sure that on the cyclohexene, these two are cis. That's why I color-coded them. Since these two substituents coming off of your diene are both in Z, you got to make sure that these are both in the same either wedge or dash. There you go. Okay. Let me finish it up. C and C and there we go. Let me just like change it up for you. If I had, okay. So let's just two things. So why did I put them all on the wedge? So I was totally able to change it up, right? So these on CN, or these on the wedge. So just compare those two groups that we're talking about. On your Dienophile, these are the ones that you have to compare to each other. So since they're cis, they should be on the same either dash or on the wedge. If they were trans, one has to be on the dash, one has to be on the wedge. If the second thing is on the diene, since we had Z and Z, we had to have them both on the same thing. So we did the wedge here. If we had E and Z, one would be on the wedge and one would be on the dash. And there's lots of possible products for this because there's a number of stereogenic centers on this. And since there's a lot of stereogenic centers on this, there's a number of products that you can draw. So I don't think she's going to be too picky about this. I don't think she's going to give you something as hard as this. But if she does anything you draw, if you compare the right things to each other, you'll be fine. Again, you can ask me questions on any of these in office hours or after any of my lectures. Okay. For this one's a little bit harder. Okay. Let's do this. I have some notes here that I would like to share. I didn't really give myself any room. Let me just put it here. A tip for identifying whether we have an electron withdrawing group or an electron donating group is to draw benzene ring derivatives. So let me put that in. Draw benzene ring derivatives using the given functional group. So whatever functional groups they give you here. Using given functional groups. To help figure out if we have electron donating group or electron withdrawing group. Okay, cool. So an example of this is for like let's call this A, right? So for A, I'm going to draw a benzene derivative A, which is drawing just the benzene and attaching this group to it. So, and this just means you can either put an NH2 or an NR2, the R's being carbon chains, or an H and an R. It's just like the possibilities that it could be coming off of the amine. I'm just going to do them both H2. Just doesn't really matter. Okay. What you should note is when you have lone pairs directly on the benzene ring, just like this heteroatom does, this is a heteroatom that has lone pairs right next to the benzene ring, you're able to resonate them into the benzene ring. And so because of this, I'm able to tell whether we're donating electron density or withdrawing electron density from our groups, from our benzene ring. So here, I drew my resonance structure after I drew my benzene derivative. And so this tells me that my amine group gave electron density towards my benzene ring. And how we would know that is because check the resonance out. We formed a carbanion. We're giving electron density to the benzene ring. We're pushing it to it. So then, since we're giving it electron density, we know that this is an electron donating group. Okay, let's try that with some other ones. Let's try that with this one, because I know this one is going to give us the same thing, basically. Draw your benzene ring derivatives just to help you out. If you do this for all of them, you're going to be able to like pretty much memorize what's an electron donating or electron withdrawing. So I would tell you like you should practice this. So I attach it to my benzene ring and I notice that they have a lone pair that I can resonate into the benzene ring. So my resonance structure has a carbanion, right? So again, donating electron density, so electron donating group. these will be the same thing. Oh, I'm actually going to do this one first because I want to show you something very cool. I'm draw the resonance structure. I have a lone pair directly, like right next to the benzene ring, so I'm able to resonate inside. And so my resonance structure gives me a carbanion, telling me that I'm donating electron density. So again, electron donating group. Okay. I'm looking at these two now. I'm comparing these two since they look so similar, but the formula is, or like, yeah, the formula is telling you they're oriented in different ways. So the carbon atoms are in different positions and everything. So what I'm going to do is, again, I'm going to draw my benzene derivative. Oxygen is next to the benzene ring, then it's a carbon double bonded to an oxygen, and then R. We still have a lone pair right next to the benzene ring, so resonate inside. Form your carbanion, so we're donating electron density. There you go, electron donating group. Okay, now we try this one over here. Draw my benzene ring derivative. This time the carbon right on the benzene ring is a carbonyl. And we still have an ester, but it's flipped around. And so there doesn't look like there would be much of a difference, but there is. Notice how there isn't an available lone pair on the atom right next to the benzene ring. So this time, instead of resonating in, we're resonating out. Breaking this double bond and forming it on this side. My resonance structure now looks like this. We formed a carbanion. So since we formed a carbanion, we know that we're withdrawing electron density away from the benzene ring. It shows us that it's withdrawing. So then I'm going to put electron withdrawing group. So it does matter how you orient your atoms. And so again, the main thing to look at is whether you have a lone pair directly on the benzene ring. And so these next ones are kind of harder. For NO2, you need to know what the structure of NO2 looks like, and this one's going to be kind of weird. So notice how there's no charge over here, right? It's neutral. But on the Lewis structure that I'm about to draw, there is going to be a charge. There's a minus charge on my oxygen because it only has one bond and 3 lone pairs around it. There's a plus charge on my nitrogen because it has 4 bonds on it. So these two cancel out, and then notice how it doesn't have a charge on it because they're canceling out. So just know the structure, and that'll help you pretty much with determining whether it's electron donating or electron withdrawing if you don't remember on the test. And so again, we don't have an available lone pair because this is a positive nitrogen, so it doesn't have available ones. So we're resonating outwards, breaking that bond, resonating outwards. And my resonance form should look like this now, with a carbocation. Oops. Let's see if we're good here. There we go. Another thing to look at is make sure, like, this is just like a side note on your resonance structures. If you originally have a neutral molecule, so like on this top structure, we had a positive and a negative charge and they cancel out, so it's neutral. On the next resonance form that you draw, that should be neutral as well. So we have plus, plus, minus, minus, it cancels out. And we have a neutral charge. So I was about to make a mistake right here because of that. Okay. But again, notice how we're withdrawing electron density from the benzene ring. So electron withdrawing group. Again, we should know how this one is drawn. Touch it to S, double bond, OH. So there's no available lone pair on the sulfur atom. So I'm going to break it and resonate it outwards. My resonance form should look, or should have, a carbon ion on it. Cool. So since we have a carbocation, sorry, we're withdrawing electron density, and this is an electron withdrawing group. This next one, CN. Let me change my color so that didn't blend in with everything else. Carbon nitrogen double bond. I'm gonna draw my resonance form. We have no available lone pair right next to the benzene ring. So what I'm gonna do, I'm gonna break this bond, put it right here. We can't have 5 bonds to my carbon after I resonate, so I'm gonna break this bond and put it right here. So my resonance form should look like this now. There we go. Withdrawing electron density because we have carbocation on the benzene ring. So electron withdrawing group. And then the 2 exceptions. So notice how everything here I've been drawing resonance forms. So there are electron donating groups or electron withdrawing groups because of the resonance. For these next 2, so this X is a representation of halogens, so like chlorine, bromine, iodine, and stuff. If you think of the periodic table, the halogens are on the right side, and we know that the trend on the periodic table is you go towards the right and upwards. You get fluorine on the very top, right? Top right. And so we know that fluorine is the most electronegative atom. And so anything going in that direction is going to be electronegative. So my halogens are actually electronegative. And so we're not going to be able to say like it's an electron withdrawing group, because it is an electron withdrawing group, but not through resonance. It's going to be through the inductive effect. For the reason that our halogens are electronegative, so they're pulling away electron density through the inductive effect. For my R groups are like carbon bonds. So what you should know about carbon is that it's electropositive. Electropositive is the exact opposite of electronegative. Electronegative likes to pull electrons to itself. An electronegative atom likes to pull electrons to itself. Whereas an electropositive atom, if I'm a carbon, I like to push it away. So if I'm pushing away, I'm donating into my benzene ring. So I'm going to draw my benzene ring derivative. So we got toluene here, that's what it's called. This R group is going to be pushing away electron density into the benzene ring, not through resonance, but through the inductive effect. So electron donating group through the inductive effect. So let me draw the dipole here too. There we go. Oops. Cool. This next one. For each of the following compounds below, draw a representation showing all of the p orbitals. Determine if each compound is conjugated. For the conjugated compounds, circle the atoms involved in conjugation. So all I'm going to do, there was like a lot of instructions there. All I'm going to do is highlight my sp3 atoms, or my conjugated. I'm going to highlight my sp3 atoms, and then I'm going to label under it if it's conjugated or not. So here we have an sp2, 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 sp2. And so side note, carbocations, carbanions, and radicals are also in sp2. So then this carbanion that we have right here would also be considered sp2. So I'm going to label this one as conjugated. Then we go over here. One of the key things is pretty much knowing or labeling how many hydrogens you might have on a carbon bond, right? So since this carbon has those four bonds to it, nothing can resonate on it or anything. Down is sp3, so we don't even mind that one. But this carbon is sp2, this carbon is sp2, and this carbon is sp2, as well as the oxygen is in sp2 form. So then here we are conjugated because we have 3 consecutive sp2 atoms. So conjugated, not completely conjugated, but conjugated nonetheless. Here we have sp2, 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 sp2. We have 4 consecutive conjugations, so not completely conjugated compound, but we're conjugated. Again, here, labeling your hydrogens would help you out, like to figure out whether it's sp2 or not. That one is sp3, but this is sp2, sp2, sp2. And again, carbon ions are sp2 as well, because they're able to resonate. Those lone pairs are able to resonate. Then I go down here, highlight all my sp2 atoms. We're completely conjugated here. All of my compound is conjugated. I'm going to call this one isolated. There you go. Actually, wow, why did I do that? No. There was conjugation there. 3 consecutive conjugations, so this is conjugated. Here it's isolated. Because we have 2 consecutive sp2 atoms, but we know that's not what conjugation is. We need 3 consecutive sp2 atoms. And right here, we're skipping. Because it's sp3. Again, labeling your hydrogens will help you. You highlight these 2, these 2, and this one. Cool. So this one is isolated as well. I'm going to do, let me see. I'm going to do this one first. So for this one, rank the following in order of reactivity towards 1,3-butadiene. So draw 1,3-butadiene first, and it's just this right here. So in our Diels-alder, we know this is our diene. And we know that it reacts with our dienophile. This is a simple dienophile. What we should remember is that our dienophile is our electrophile in this reaction, and our diene is the nucleophile in the reaction. I was always really bad at understanding like pretty much why this was. So this is just something I had to memorize. But just knowing these 2 facts, that one is electrophile and one is nucleophile, helps you understand what makes it more reactive or not. So nucleophiles, it has the negative charge on it and the symbol, Nu, negative. So we know that it likes to have a lot of electron density. So some substituents on the diene who are electron donating will give the nucleophile all the electron density it wants. So my dienes prefer electron donating groups, whereas my dienophile, we're an electrophile. We like to be positive. So if we have a substituent that withdraws electron density from us, we love that. So then I'm going to do dienophiles prefer electron withdrawing groups. Right here, it's asking us to rank the reactivity, the following in reactivity towards 1,3-butadiene. So we're talking about Diels-alder here. We're asking you to decide on the dienophile. Which dienophile is going to react fastest between A, B, and C? So my first step for this one is identifying electron donating or electron withdrawing groups. I don't know why it printed it out so close to each other, but all we have to do here is see whether or not we have a lone pair close to our double bond. On this one, we do have a lone pair, so we know we can resonate it inwards. So it's donating electron density. If I were to draw the resonance structure for this one, it's donating electron density to the double bond. So then we have an electron donating group on this side. It looks weird, right? Because it's in like a chain. But this is your dienophile. It's just one double bond. So it has two electron donating groups on it. Then I look at this next one. It has no available lone pair right next to the double bond. So we're resonating outwards. And if we resonate outwards, if we drew the resonance structure for B using these arrows that I just drew, we would have a carbocation where the double bond used to be. That means it's electron withdrawing. And we actually have two electron withdrawing groups on it, because we have two carbonyl groups on our compound. This next one is electron donating by the inductive effect. So this is a weaker electron donating group compared to everything else, because resonance is like something that really provides stability and everything, something very strong, in compared to inductive, which is kind of like the softer version, very like sharing kind of sharing. Okay, so then we're talking about reactivity of our dienophile. Our dienophile likes electron withdrawing groups, so to determine which one is best, or it's easy to determine which one is best right now. So the one that would be the most reactive is B, because it only has electron withdrawing groups on it, whereas A and C have electron donating groups. Okay, so between A and C, which one would react as, or would act as, which one would we label number 2? React kind of faster than the other. And I would say that C would react as number 2. And that one would have the least reaction. And this one is kind of like, it confused me at first, but then you think about it. So we prefer electron withdrawing groups, and if we can't have an electron withdrawing groups, we want as little electron donating groups as possible. So if we're donating through the inductive effect, that's a pretty small amount of donation. So that's why we would say, okay, number 2 would react the second fastest. Whereas I'm sorry, C would act as the second fastest. Whereas A has 2 electron donating groups that are donating through resonance, which is a lot more donation. And we don't want electron donating groups on it. So then it would react the least. I'm briefly skipping over that other one. I'll include this one and this one on the next worksheet. But let me just finish with this. Rank the following in order of increasing energy released per pi bond, reduced by the heat of hydrogenation. 1 being the greatest, 4 being the least amount of energy. Okay, so one thing that we should note is that something that releases least or low energy is something that is stable. And something that releases high amount of energy is something that is unstable. So I like to think of like a crazy person. So a crazier person would be very unstable, would release a lot of energy. Whereas someone who is more calm, more stable, releases lower energy. That's how I remember it. So then here, notice that we have like a pretty much the same compound with a bunch of double bonds in different places. When you see something like this, and when we're talking about stability, we're basically asking you to see whether it has conjugation or not. And so you're going to find that some of them have conjugation, but what really matters is consecutive conjugation. So notice how we have 1, 2, 3, 4, 5, 6, 7, 8 consecutive sp2 atoms. Whereas on this one we have 1, 2, 3, 4. So we still have conjugation, but not as much, not as stable as A, because we're skipping. More conjugation here. Okay, yeah. So we're pretty much just skipping here. I'm going to put all the things that aren't conjugated in blue. So pretty much what we're skipping in. Highlighting this in highlighting in yellow all my sp2 atoms. Okay. So I'm going to do A is my most stable because it has a lot more consecutive conjugation. Then I'm going to do D is my second most stable. Okay, let me do my least stable first. My least stable is going to be the one that is completely isolated. So C has no conjugation whatsoever. It's isolated, so it would be unstable, a lot more unstable or it would release more energy. When you hydrogenate it. And so again, least amount of energy will be A, so 4. Will release the most energy will be C, 1. We'll label D as 3 because it still has 1, 2, 3, 4, 5, 6 consecutive conjugations, whereas B has 1, 2, 3, 4. So we'll label B as 2, and our most stable one as 1. Okay, good with this one. Good with this one. And then what heat of hydrogenation means is again the same thing as last time. You have these double bonds. You have H2 palladium on carbon, and that's hydrogenating it. So adding the hydrogens to the double bonds, so that the double bonds go away. So pretty much the same thing as what we did in the first step. This last one has to do with the previous problem that we were talking about. So using the molecules from the previous question, match the relative absorption to the correct compound. Write the letter under wavelength. Okay, so they're giving you 4 wavelengths here. And one thing that you should note is that energy is inverse to wavelength. This is like the key. So that means if energy is high energy, that we have a low wavelength. And that makes sense, right? Because gamma rays are very high in energy and they're very low in like wavelength, yeah, nanometers. And so that'll be what our base is, what we base it off of. So all we have to do here is assign which wavelength goes to A, B, C, or D. So something that is unstable, high in energy, like my isolated in C, is going to have the lowest wavelength. So then I'm going to say that this right here is C. And then you just keep going from there. Second lowest in wavelength is B. Third lowest in wavelength is D. And the highest in wavelength, so remember high wavelength equals low energy. We said our lowest amount of energy would come from our most stable compound, which is A. There we go. All right, so it looks like we're done with pretty much most of this worksheet. Again, I'll send out a copy of this worksheet so you can work it out as you go through the video. And I'm going to leave off the HBr and the labeling hybridization of the heteroatoms for our next worksheet. Okay, cool. I'll see you guys later.